Phase 1 of the Starlink constellation consists of 1,600 satellites, arranged into 32 orbital planes, with 50 satellites in each plane. Because of the orbits, coverage density is much greater in latitudes near 50 degrees north than it is near the equator. The satellites are all at the same altitude, so an important property is the phase offset between orbital planes. If you get this wrong, the satellites collide, which would be bad. Simulation shows that the best phase offset is 530 seconds. Looking upwards, there are many satellites overhead at any one time. The SpaceX FCC filing indicates that satellites are reachable down to as far as 40 degrees from the vertical. At more northerly latitudes, this can give 30 satellites overhead and reachable at any time. There are 5 laser links per satellite to communicate with other satellites. The satellites ahead and behind on the orbital plane stay in the same place in the sky, so these are good candidates for the first 2 laser links. Satellites in the neighboring orbital planes are also fairly static, whereas satellites in crossing orbital planes pass by at 7.3 kilometers per second. As much of the population stretches around northern temperate latitudes, more long-distance communication goes east-west, so makes sense to connect to neighboring satellites to the east and west, rather than to the nearest neighbors. This leaves northeast-bound satellites talking to their neighbors and southeast-bound satellites talking to theirs. We'll use the final laser link to communicate with satellites in crossing orbital planes. Here we can see how all the side links align in an east-west direction, providing good east-west paths. This is all 5 links in action, giving good paths in almost all directions. Let's try connecting from New York to the most directly overhead satellite, then via the lasers to the satellite most directly over London, and then down. We're running Dijkstra here at 10 frames per second, using link latency as the metrics. The round-trip time is less than current internet paths, though it's higher than it would through optical fiber laid along the Great Circle route. The latency is also quite variable. While routing to the most directly overhead satellite maximizes RF signal strength, it isn't great for latency. Routing up, and then across, involves a dogleg path. Also, one ground station often connects to a northeast-bound satellite and the other to a southeast-bound one. You want to avoid this if you can. It's much better to route the RF links and the laser links together. We add all the possible RF uplinks to the network graph, and run Dijkstra's algorithm over the end-to-end network. This gives significantly lower latency, and it is less variable too. New York to London now takes about 50 milliseconds. San Francisco to London takes about 80 milliseconds, which is quite a bit better than the best theoretical optical fiber path. London to Singapore takes 93 milliseconds. Generally, the further you go, the bigger the gains over using optical fiber. One route that doesn't work quite so well is London-Johannesburg. As we didn't provide any direct north-south links, this has to zigzag its way. The latency is a lot better than the current internet, but we should be able to do better still. Beyond the best path, there are other good paths we can choose. If we remove all the links on the best path, and rerun routing, we can find many more paths that all have fairly good latency. Here are the 4 best paths. Even 10 paths work fairly well. Can we do 20? No, but we can do about 15. What can we do to improve north-south connectivity? This is where Phase 2 of the constellation comes in. This adds another 1,600 satellites in 53.8-degree inclination orbits. They orbit slightly lower than the Phase 1 satellites, so travel slightly faster. How should we best use the side lasers? Connecting to the equivalent satellite on the next orbital plane gives long links. Staggering the links by one doesn't add much we don't already have. Staggering the links by two gives pretty good north-south routing, at least at higher latitudes. Turning on all the lasers on these additional 1,600 satellites, we get links like this. Of course we wouldn't operate these by themselves, they operate along with all the Phase 1 satellites. Now the London-Johannesburg path looks much better, latency has improved by 20% and is also much less variable. Even the New York to London paths now have slightly lower latency, as there are more paths available. The constellation is now so dense that we have no difficulty finding 20 pretty good paths, all with better latency than the current internet. The 5 best are all really good. Finally, there are the satellites in high inclination orbits. One role of these is to provide coverage for Alaska, as this is an FCC requirement. They also provide a limited number of paths over the pole. Sometimes this is the shortest route for very long-distance traffic. Let's add in all 4,425 satellites now. New York to Beijing is one route that benefits from traveling over the Arctic, though the wind isn't all that large, and sometimes the orbital planes don't quite align well enough. When this happens, routing goes via a lower inclination path. That concludes our presentation of low-latency routing on the Starlink constellation. In addition to providing coverage no matter where you are, we can also see that with careful choices of laser orientation and routing, it provides the potential to greatly reduce latency for long-distance internet traffic.